Okay, I will start. Okay, hope you can see me and hear me very well. Okay, so uh, so in this course, okay, so our course is this one, applied circuit analysis. Okay, so already you have uh, uh, 4 lecture note added to the LMS. You can download and read them. So, okay, so this is the first lecture is regarding the uh, resistors. Okay, so Ohm laws and Kirchhoff laws. Okay, so I think you can refer it and you can refresh your memory by yourself. Okay, you can refer this lecture also, like a recorded session also. Okay, so in this course mainly we are focusing on LRC circuit. Okay, so here, so this is our uh, subject, applied the subject name, applied circuit analysis. Okay, applied circuit analysis, applied circuit analysis. Okay, so this is 2 credit course subject. Okay, so you have to do this in now. Okay, subject. Okay, so in this course we are mainly focusing on LRC circuit. Okay, inductor, resistor and capacitor circuit. Okay, inductor, resistor and capacitor circuit. Okay, so uh, so actually we are mainly focusing on the AC part. Okay, so here we are mainly focusing for AC analysis. Okay, alternative current analysis. Okay, not the DC analysis. Okay, so in this course you have to mainly analyze this LRC circuit in AC domain. Okay, for that, I think you can remember that LRC circuit, normally we can get a differential equation. Okay, differential equation to analyze these circuits, or we can use Laplace transform. Laplace transform, S domain. Okay, transform, that is S domain, complex domain. Okay, that is in complex domain. So basically we can use these 2 methods to analyze this LRC circuits. Okay, so we will continue the session, and I think if you have time, you better look at your old math notes. Okay, math note, and refresh your memory on these 2 uh, cases, differential equation and Laplace transform. Okay, so I think if you know first order and second order differential, how to solve a first or second order differential equation, that knowledge will be enough. Okay, so anyhow we will continue and we will see what happened there. Okay, so so we start our study in the capacitor, from capacitor. Okay, because I think we have already know about the resistor. Okay, resistor, that is ohmic load. Okay, that is ohmic load, or we can say it is a linear load. Okay, linear load. Okay, linear load means that VI characteristic is linear. Okay, so if you plot the voltage with respect to the current I, okay, so you know that voltage is this is the voltage difference. It is measured by volt. Okay, and the current is measured by ampere. Okay, I think you can remember that one. Okay, so VI characteristic is somewhat like this. Okay, so that means if we have a resistor, okay, and if we give a voltage across the resistor, okay, when we increase the voltage, okay, the current is linearly increasing. Okay, current is linearly increasing across this resistor. Okay, so that is why resistor is called a linear load. Okay, so it is a linear component. Okay, so if we have I think you can remember that if we have several resistors in series, okay, so the resultant is the resultant resistor is the sum of each resistors. I hope you can remember these things, and I hope you can derive these things, okay. And if the resistor is parallel, so this is series resistor equivalent resistance, okay, series equivalent resistance, or if the parallel, okay, so it is, we can say that it is equal to the 1 by that resistance, okay. So it is 1 by resultant parallel resistor is equal to 1 by R1 by 1 by R2, like this, okay. Okay, so this is the resultant resistors, okay. And I think if you want to measure the power across this resistor, okay, we can use this power is equal to, you know, that VI, okay, voltage into current, okay. So you know that V equal IR according to Ohm law, okay. So you can replace this V or I using this equation, okay. So you can say like this, okay. So if you substitute V, if you substitute IR instead of V, you will get I square R, okay. And also, if you substitute I instead of V, if you substitute of so I is equal to V by R, no, according to this one, you can say that I is equal to V by R, okay. So if you substitute this V by R instead of I, you will get, okay, so this is equal, you will get V square divided by R, okay. So this is the power across the resistor, okay. So I think you already remember these things, okay. If not, kindly refer your old notes, okay. Okay, anyway, we will start our study from the capacitor, okay. From the capacitor or condenser, no, also called as condenser, okay. So capacitor is not a linear device, okay. It is a non-linear device, okay. That means it is not depend on, or it is not characterized, we can't characterize this using the Ohm's law, okay, because it is a non-linear device, okay. So it is we can't characterize it using the Ohm law, okay. So I think you already know what is a capacitor, okay. So it is just a two plate, okay. It is just a two plate, and between these two plate, these are conductor, okay. These are conductor, maybe copper plate, most probably copper plate, okay. And it is divided by some dielectric material, okay. So between these two conductor, there is a dielectric material, okay, dielectric material, okay, or substrate. We sometimes called it substrate, okay. And I think you know that, okay. There is one parameters. We normally referred it using epsilon, okay. So this is we called electric permittivity, or sometimes called dielectric constant, okay, permittivity, okay. For example, if the air is here, okay, if the air is here, this dielectric constant or electric permittivity is equal to 1, okay. If the air is there, okay, for air, this epsilon is equal to 1. Okay. So I think you can remember this. Okay. And I think we also define this epsilon dielectric constant as epsilon naught, epsilon r. Okay. So this epsilon naught is, sorry, it is, this is not, sorry, I'm sorry. Okay. For air, epsilon is not equal to 1. I'm sorry. It's a mistake. Okay. For air, epsilon is not equal to 1. There is a value. Okay. I can't remember the value. Okay, maybe we can see it in the internet. Let's see. So let's see. Dielectric constant. Okay, or electric permittivity. Okay, constant of air. Okay. So you can see that there is a value. Okay. So actually, this is also depend on, no, it is not depend on the frequency. That is a constant. Okay. So we will see the Wikipedia. Okay. So I think you can remember these things. Okay. We have learned this in electric field in A level also. Okay. So I think this is the value. Okay. This is the value for air. Okay. The epsilon value for air, normally it is denoted as epsilon naught. Okay. So, okay. So this is the value. Okay. It is very small value. Okay. I'm sorry. Okay. So, so normally this epsilon naught is the dielectric permittivity of air. Okay. Dielectric, dielectric constant or permittivity, electric permittivity, permittivity. Okay. I will write it clearly. Permittivity. Okay. So this is the permittivity of air. Okay. Permittivity of air. Okay. So there is a value, no? 818 divided into 10 to the power minus 12 or something. Okay. So there is a value. Okay. So that value is the dielectric constant of the air. Okay. And also we have defined this epsilon r. This is called the relative permittivity. Okay. So this epsilon r is referred as relative permittivity. And we can define epsilon as epsilon naught into epsilon r. Okay. So sometimes epsilon is defined like this. Okay. So many substrate, this value is given in the data sheet normally. Okay. So normally we are given the relative permittivity. Okay. Not the permittivity. Okay. So normally we are given the relative permittivity, relative dielectric constant. Okay. So if we want to find the exact permittivity, we have to multiply it using this permittivity of air. Okay. So I think it is clear. Okay. Have you any question up to this?
Yes, sir. Is there any unit for the permittivity?
Yeah, it is, as I can remember, farad per. Okay, I will tell you the unit. Okay, we are going to get the expression. Okay, at that time now I can't remember it. Okay, at the expression I will tell you what is the unit for permittivity. Okay, just give me a moment. Okay, so we will come to that point. Okay. Okay, so there is a unit. Okay, to measure this one, there is a unit. I will tell you what is the unit. We will come to that point. Okay. Okay. So so basically conductor is a two conductor. Okay, two conductor, and between that two conductor there should be a dielectric constant. Okay, so that is a normally a capacitor. Okay, so we will see the operation of the capacitor. Okay, so you know that okay, so here we have one plate and here we have another plate. Okay, so here we have a dielectric constant, dielectric material, maybe air or any dielectric material. Okay, so if you connect this plate, okay, this plate to a battery or something, okay, so this plate will get some charges. Okay, so if you connect this plate to plus side of the battery like this, okay, so you have connect this plate to the plus side of the battery. Okay, this plate will get plus charges. Okay, so this plate will get plus charges. Okay, and this plate will generate minus charges. Okay, so if we are given a plus voltage here, okay, plus voltage here, it will charge as plus. Okay, and this one is charged as minus. Okay, so this is normally happen. Okay, so it create a electric field from this plus to minus. You know that electric field is plus to minus. Okay, I think these things also we have learned in our A level. Okay, A level physics. Okay, so this is the E field. Okay, and you know that. Okay, the E can be defined. Okay, E can be defined as if so. You can see that there. So this battery has a voltage difference. No, okay, voltage difference. So if you give a voltage difference between these two plates, these plates are charged. Okay, these plates will get some charge, and this one is plus and this one other plate will be minus. Okay, so there should be a voltage difference also. There should be a voltage difference between these two plates. Okay, and this is plus voltage and this is minus voltage, and voltage difference also in this direction. Okay, so E can be defined as, okay, voltage divided by the distance. Okay, so if the distance between this plate is D, okay, so E is equal to V by D. Okay, I think we have learned this equation, okay, in our A level maths. Okay, so I think you better remember this one. Okay, E is equal to V divided by D. Okay, and so the distance between these two plates is D. Okay, so distance between these two plates is D. Okay, so this D can be measured in meter. Okay, and V can be measured in volt. Okay, 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 and I think there is another definition for E. Okay, there is another definition for E. So you know that in A level we have learned that E is equal to 1 by 4/5 epsilon naught epsilon r. I can't remember this is correct or not. Okay, as I can remember it is 4/5. Okay, and the charges Q1, Q2 divided by R square. Okay, so that is if the 2 points are there, Q1, Q2, okay, and the distance between these 2 points is R, okay, so electric field due to this charge on this charge, due to this charge on this charge, or due to this charge on this charge, okay, the two are same, okay, can be expressed using this equation. Okay, so this is we have learned in our A level maths. Okay, A level maths, and you A level physics, sorry, and you can derive this one, this equation also using this one. Okay, so derivation no need, just remember this. Okay, I think you are already familiar with this one. Okay, and also E can be expressed as, okay, E can be expressed as, so you can see that here we have some charges, okay, we have some charges, okay. So normally charges is measured by coulombs, no, it is measured by coulombs, C, okay. So if there are q charges, okay, if there are q charges, so this is the charge value, okay, number of coulombs, okay, number of coulombs, okay. So I know that you know that for a proton there is a certain value for the charges, okay, it is measured by coulomb, okay. And if there are 10 protons, okay, you can find the total coulombs by multiply 10 from that 1 proton coulomb, okay. So if you, I think in internet you can find that value also, okay. So if you find the what is proton plus charges, we called as proton, no, proton charge value or something. Let's try charge value. Yeah, value is there, no? Sorry. Right. Yeah, I think this one. Okay, so this is the charge value for 1 proton, okay. So that is measured in coulomb, you can see that, okay. So if there are 10 protons there, okay, if there are 10 protons in this plate, okay, if there are 10 proton in this plate, and there should be 10 minus charge, that is we called electrons, okay, and 10 electrons should be there, okay. And the proton and electron charge are same, that is same, but this is a plus charge and electron has a minus charge, okay. So in the value is same, magnitude is same, okay. I think you can remember, okay. So if you want to find the total coulombs, total charge value, okay, you can multiply that 1 proton value, that is 1 to the 1.6 10 to the power something, I can't remember. Sorry. 10 to the power minus 19, okay, 10 to the power minus 19, and you can divide, you can multiply it by number of protons, okay. If the number of protons is 10, so this is the total coulomb value, okay. So total coulomb value, okay, if you have total coulomb value, okay, and it is divided by the total area of this coulomb, okay, of these charges, okay. So in this case there is a plate, no, so there is a plate like this, conductor plates, and there are some charges distributed in this plate, okay. So we have area, okay, so we have area here, okay. So if you know the total coulombs, okay, total coulombs, and if you divided it by the air, okay, that means coulomb per 1 area, coulomb per unit area, Q divided by A, okay. And this E also affected by the epsilon, this value, epsilon, okay. E also affected by the epsilon, okay. So epsilon, so epsilon is also affected by the epsilon, and Q divided by A and multiplied by epsilon, again you will get an expression for E, okay. So if the electric field, okay, so if the plate is there, electric field is equal to V divided by D, okay, voltage difference and voltage difference divided by the distance between 2 plates, okay, and again is equal to the total charges divided by epsilon into area. Okay, so this epsilon is the dielectric constant of this material. Okay, the material between these two plates. Okay, so this equation is also there. Okay, this is the first equation and this is the second equation. Okay, so is this okay? So we have these two equations. Okay, related with the electric field between these two plates. Okay, so I think it is okay. So if you have any problem, you can ask. Okay, okay. So now now so this E is the electric field between these two fields. Okay, so if I equal this, so this E and this E should be same, no? The E field should be same. The E field value should be same. Okay, so if I equal this to, if I equal this one equal to, okay, I will get V divided by D is equal to Q divided by epsilon A. Okay, is this okay? Okay, so you can get this expression. Okay, and by this expression you can get that. Okay, I will get like this. Okay, I will get this V here. Okay, V here, and this epsilon A is here. Okay, so I can do like this, no? Okay, so I will write this term first. Okay, so Q divided by V is equal to epsilon A divided by D. Okay, so what is this value actually? Okay, so so actually you can derive. Okay, you can derive a unit. Okay, using this expression for epsilon. Okay, so if you derive that one, okay, so you can see that epsilon is equal to, okay, epsilon is equal to Q D V A, no? Okay, epsilon is equal to Q D V A. Okay, so using this expression, you can get unit for permittivity. Okay, so Q is measured by Coulomb and D is measured by meter. V, voltage, is measured by volt, and A is measured by square meter. Okay, so you can see that you can have one and you can get C minus M minus 1. Okay, so this is one unit for epsilon. Okay, this is one unit for epsilon. Okay, and I think you can get other value also. Okay, so you can get other values also, other unit also. You can derive other unit also, because this is not the, this epsilon is not the basic parameter. Okay, අපි level වල ඉගෙන ගන්න මොකද්ද මූලික ඒකක කියලා. Okay, the distance, time. Okay, so those are the fundamental units. Okay, but this unit can be derived using those fundamental units. Okay, so so I think this is one unit. Okay, so you can use this unit also. Okay, and for this V also you can find another unit, no? Okay, this V also, this is a voltage difference. Okay, and this V can be get by you can use other units. Okay, to derive this V voltage. Okay, and Coulomb and meter you can't get other values because these are fundamentals one, but this for V you can get other value also, and you can derive another units for epsilon 1. Okay, and this is 1 unit for epsilon 1. Epsilon. Okay, is that clear? කුමාර ඒක ඕකේද? තේරුණාද ඒක?
ඔව් සර් දෙන්න.
ඒක තේරෙනවනේ. දැන් මෙතන epsilon කියන එක අර ෆන්ඩමෙන්ටල් එකක් නෙවෙයි. එතකොට එයාට අපිට ගන්න පුළුවන් ගොඩක් units. හරි? දැන් මෙතන කූලෝම් කියන එක නම් ෆන්ඩමෙන්ටල් යුනිට් එකක් මට මතක හැටියට. හරි? මීටරුත් ෆන්ඩමෙන්ටල්. එතකොට මේ දෙක ආයේ වෙන ඒවාකින් ඩෙරිව් කරන්න යන එක තේරුම්ක් නැහැ. ඒ වුණාට වෝල්ටේජ් කියන එක ෆන්ඩමෙන්ටල් එකක් නෙවෙයි. ඒකට අපිට එක එක මේවා ගන්න පුළුවන්. හරි? එතකොට අපිට පුළුවන් තව මේ epsilon වලට වෙන වෙනම යුනිට් ගන්න. හරි? හරිද තිබ්බේ මොකද්ද යුනිට් එක මනලා? Wikipedia එකේ. Let's see it by electric constant of air. Wikipedia. Yeah, it is farad per meter. Okay, so it is measured in farad per meter. Okay, I think you can. Okay, I will come to that point also. Okay, so using this one. Okay, so using this one, we can measure. We can get another one also. Okay, so I will come to that point. Okay. Okay, so let's continue our discussion. Okay, so we get this expression. Okay, so Q divided by V is equal to epsilon A divided by D. Okay, epsilon A divided by D. Okay, now what is this value? Okay, so can you tell me this value? Okay, so we can change this voltage. Okay, we can change this voltage, and according to change of this voltage, the Q, the number of charges also will be changed. No, that is clear. No, okay. So if you connect a large battery between these two plates, okay, so this Q will be increased, the charge will be increased. Okay, so when we increase the voltage, the charge will be increased, and when we decrease the voltage, charges will be decreased. Okay, so practically we can understand that now. Okay, so if this Q is increasing, V is increasing, and Q is decreasing, V is decreasing. Okay, so that is the normal way. Okay, okay, so what about this one? Okay, what about this? Okay, so look at this expression, look at this part. Okay, so you can see that this is epsilon, that is the dielectric constant between the plates. Okay, and A is the area of a plate. Okay, A is the area of the plate. Okay, and D, the distance between the plate. Okay, so if you didn't change the dielectric constant between these two plates, or if you didn't change the area, and if you didn't change the D, distance. Okay, so this is a variable or constant. It will be a constant, no? Because we are not going to change epsilon, area, or distance. Okay, okay, so if these are not changed, this will be a constant. Okay, so this will be a constant. Okay, constant. Okay, and this constant is referred as the capacitance. Okay, capacitance. Okay, so this epsilon A divided by D normally referred as the capacitance. Okay, so you can see that capacitance is a constant. Otherwise, okay, if not, we change this epsilon A or D. Okay, so if we didn't do any modification to these plates, okay, in other words, if we didn't do any physical modification for this conductor, for this capacitor, okay, so the capacitor, so I can tell this unit as a capacitor. No, it is a dielectric constant sandwiched between two conductors. Okay. So if I didn't change, if we do not change the uh, physical structure of this capacitor, okay, this will be a constant, no? Okay. තේරුණානේ එක අපි ඒකේ dimension එකට හරි අර permittive කියන්නේ ඇතුලේ තියෙන dielectric material එක හරි වෙනස් කරේ නැත්නම් මේක අනිවාර්යයෙන්ම constant එකක්. එයා වෙනස් වෙන්නේ නැහැ. It will not change. Okay. So, and it is referred as capacitance, or it is defined as capacitance. Okay. So, this capacitance is a constant if we do not change the physical structure. අපි structure එක වෙනස් කරේ නැත්නම් ඒ කියන්නේ එක්ක area එක, එක්ක distance එක, එහෙම නැත්නම් dielectric material එක change කරේ නැත්නම් it will be a constant. හරි. Okay. So, we can define this one, C equal to Q divided by V. Okay. This one. Okay. And this C is equal to this one. Okay. Epsilon A divided by D. Okay. And this C is equal to this one. Okay. I don't think you need to remember all these equation. Okay. So if you are given a paper, okay, so this equation will be given. Okay. But the most important thing is you should understand this equation, and you have to apply them when required. Okay. Okay, so that is enough. You no need to remember all this equation. Okay. So normally for a final paper or any assessment, you will be given this equation. Okay. Or otherwise it will be open book test or something. Okay. So basically you no need to remember these things, I hope. Okay. So C is equal to Q divided by V. Okay. So capacitance can be defined in other way. Okay. So how can we define the capacitance? We can define that it coulombs or charges per unit volt. Okay. Unit volt. If you given a unit 1 volt voltage difference, okay, so number of charges induced there is referred as the capacitance. Okay, in other words, it is charge per unit volt. Okay, so this the C unit, okay, measured unit of this C is equal to Q is measured by coulomb, V is measured by voltage. Okay, so the unit for this capacitance is coulomb per volt. Okay, coulomb per volt. Okay, and this is referred as farad. Okay, this is referred as farad. Okay, so you can see that here coulomb for unit volt also can replace by farad. So you will get farad per meter. Okay, so this is the unit that mentioned in the Wikipedia for epsilon. Okay, so you can derive that one also. Okay, ඒක හරි නේද සරත් කුමාර්?
Oh, sir, that yeah.
Okay, so this is the capacitance. Okay, this C refers to the capacitance. Okay, and this C is coulomb. Okay, this C is coulomb. Okay, so that is C. This C is always confusion. No? So that is why this C divided by V is referred as farad. Okay, so normally this is the unit for capacitance. Okay, so this is the unit for capacitance. Okay, so for a different capacitor, you will have different capacitance value. Okay, 30 microfarad. Okay, 10 millifarad, 10 picofarad. Likewise, you will have some value for different capacitance. Okay, so I think that is clear. Okay, Okay. Okay. So, okay, I will again draw a capacitor, okay, in this direction, okay, and I have connect a battery between these two capacitors, okay. Let's say that I have connect a battery, okay. So this is the plus and this is the minus, okay. So at the beginning, okay, a current will flow through this, okay, in this direction, okay, in this direction. So normally current is from plus to minus, no? Current is from plus to minus, okay? And due to this current, okay, this plate is charge induced by plus charges and this plate is induced by minus charges, okay? So this is induced in on plus charges and this plate is induced in minus charges, okay? Okay, so okay, so now let's say that this E, okay, this E is changing. We are decreasing, no, increasing. We can, this is a variable battery, okay? This is a variable voltage source, okay? So let's say that this is a variable voltage source, okay? Voltage source, okay? Now, okay, now we want to find the voltage between this capacitor, okay. So now we want to find the voltage between this capacitor V, okay. So if I write the voltage between two capacitors, between this plate, okay, plate, okay. So let's say that this is not uh, variable, okay. This is not variable. Let's say that it is a constant voltage source, okay. So I think that scenario is easy to understand, okay. So this E is a constant, it is not a variable, okay. So you have connect a constant voltage source between the capacitor, okay. Constant voltage source, okay. Later we will come to the variable source, okay. Okay. At this time, we will consider a constant voltage source. Okay. So if you connect a constant voltage source between the capacitor, okay, it can be a 5-volt battery, it can be a 1.5-volt battery, it can be a 9-volt battery, anything. Okay. So it's a constant battery, DC battery. Let's say that it is a DC battery we have connected. Okay. So you can see that the current will flow through this, okay. The current will flow through this and this capacitor is charged to charge, okay. And when it is charging, the voltage, okay, when it is charging means this the the charges, number of charges will be increasing, no? That means Q is increasing, okay. Q is increasing. So you know that Q divided by V is equal to C, okay. So with respect to time, the Q is increasing. According to that, the V also should be increased, okay. That means when the time is passing, okay, when the time is passing, the charges will be increasing. In accordance, the voltage also will be increasing, okay. So this voltage is increasing according to time like this, okay. So it is not linear, okay. It is not linear. You have a curve like this, okay. You have a curve like this, okay. So it is like this, okay, like this. This is increasing like this, okay. So this is a voltage, okay. So you can see that voltage is changing with the time. Voltage is the function of time. Time is increasing, voltage also increasing, okay. So when this capacitor get it maximum charges, okay, maximum charges, it will not again charges, okay. So this battery, this, if you connect a 5-volt battery, there is a maximum charges that can be given from this battery. Okay. So when this capacitor reach to that level, it will constant that voltage. Okay, it will not increase the voltage, and it will maintain constantly. Okay, so if you normally connect the 5-volt battery, this will charge up to 5 volt, and then it is not charging anymore. If you connect the 9-volt battery, it will charge up to 9 volt. It is not charging anymore. Okay, actually, if you connect the 5-volt, it is not come to up to 5 volt. Okay, it is somewhat less than 5 volt, because the battery also has an internal resistance, and this capacitor also will have some resistance. Okay, so there is some voltage drop between these two resistance. Okay, and it is not up to 5 volt. Okay, it is something less than 5 volt. Okay, so it is depend on the what is called the internal resistance of the battery and the capacitor. Okay, now we will just ignore this too. Okay, we will ignore this too, and we will see that we say that it is come up to the battery voltage level. Okay, but it is not true. It is somewhat below this battery voltage. Okay, so it is charging like this. Okay, so you know that the Q divided by V. Okay, so you can see that Q also increasing with time. So Q is a function of time, and V also increase with time, and V also a function of time. Okay, so normally when we are, so this Q and V are variable. Okay, so I denote simple value. Okay, don't confuse. Okay, just these are varying according to time. I just use the simple letter. Okay, so this Qt divided by Vt. Okay, and this is equal to nothing but C. Okay, same thing. Okay, so I just emphasize this Q by this simple Q, that this is changing. Okay, this is not a constant, and this is changing. Okay, so that is normal standard. Okay, so you have a lecture note uploaded by Dr. Udesh, so he has used this notation. So I also use that notation. So otherwise you will get confused. Okay, so you know that this one. Okay, you know this one. Okay, so Vt is equal to Qt divided by Vt is equal to C. Okay, in other words, so if I just put these terms here and there, I can get this one. Vt is equal to 1 by C Qt. Okay, in this way I can write this one. Okay, and another thing is, okay, another thing is the current. Okay, the current between this capacitance with respect to time. Okay, current. So what about the current? What do you think about the current? How the current? So voltage is varying like this with respect to time between the of this capacitor. Okay, and what about the current? Okay, what about the current? So you can see that when we switch, let's say that there is a switch here. Okay, so we have a switch here. Okay, and if we switch this switcher, okay, if we switch this, okay, so you can see that there is no, let's say that there is no any coulombs here. Okay, so it is charging fastly. Okay, it is charging fastly. That means a current is high at that moment. Okay, so you will get a high current at the beginning, and you can see that so it will begin the charges. No, it will begin to charge this capacitor, and charges are collecting in this plate. Okay, charges are collecting between these two plates. Okay, so voltage is increasing, but this current is gradually decreasing. Okay, so it will like this because the charge is there, and that charge will affect to the voltage of this battery also. So the current will be gradually getting low. And once it's come to this point, let's say that this is somewhat T1 or something. At T1, so the capacitor is fully charged and the current will be zero. Okay. Once the capacitor, so this also T1. Okay. The same value T1. Okay. That means when the capacitor is fully charged, there is no current. Okay. And when the capacitor is begin to charge, at that moment you have the maximum current. Okay. Make up okay, neda, Kumar? This is
Oh,
okay. Make okay?
okay.
Okay. Thank you. Okay. So, so you have this voltage and current. So this current is measured in ampere. Okay. This current is measured in ampere. Okay. Okay. So, so this is, so we will come to this equation again. Okay. So what is this? This is nothing but the Coulomb or charges. Okay. So can you remember that there is a relationship between the current and the charges? Okay. There is a relationship between the current and the charges. Okay. What is that? Can you remember that? Okay. So normally current is nothing but a flow of charges, no? Okay. So if you have connect a battery between a resistor, okay. So here plus and here minus, okay. So plus charges will push by this plus voltage, and minus charges will attack, this minus value will attract the plus charges. Okay, so the plus charges is flowing through this direction, and in the same manner the electron is pushed this by minus voltage. Okay, so electron is flowing to this direction and it is attracted by the plus voltage. Okay, so electron is flowing in this direction. Okay, actually we define it as the current, no? Okay, okay, so how we define the current? Can you remember that? Okay, so if you give a voltage difference between a resistor or between a load, okay, the plus charge is going this direction. This direction is the plus charge direction, and minus charge or electron is going in this direction. This is minus. Okay, and this plus value and minus value are same. Okay, same in magnitude, but direction is opposite. Okay, so this is going, plus minus is going battery plus n to minus n, and electron will flow from minus terminal to plus terminal. So direction is vice versa, but the magnitude is same. Okay, and what is the direction of current normally we consider? මතකයිද කුමාර්? කරන්ට් එක අපි කියන්නේ මොකක් කියලාද? මේ ප්ලස් යන පැත්තට තමයි අපි කරන්ට් එක ඩිෆයින් කරන්නේ නේ. කරන්ට් එකේ ඩිරෙක්ෂන් එක. So we define the direction of current as this plus direction, plus charges flowing direction. Okay. මේකත් A level වලට අපි ගන්නවා සමහරට ඔකටට දැන් මතක නැතුව ඇති. හරි. So anyway, just memorize this that thing. Okay. So the direction of flow of plus charges is the direction of the current. Okay, direction of the current. Okay, so that is the current direction, the direction of flow of this plus charge. Okay, and what is the magnitude of the current? What is the magnitude? How we define the current? Okay, current is, can you remember that current is the charge per unit time? Okay, charge per unit time. In other words, Q divided by T. This is defined as the current. මේක තමයි basic current එකේ definition එක. This is the basic definition of the current. Coulomb, number of flowing charges per unit time. In other words, it is the rate of flowing of the Coulomb. Rate of flowing or moving the charges. Okay, so can you remember this definition? දැන් මතක් වුණා නේද මේ මේක මතකයි නේද? Okay. Okay, so current can be defined in this way. Okay, you no need to remember all these things. Okay, just try to get the idea. That's enough. Okay, so I is equal to Q divided by T. Okay, so you can see that, okay, this Q, okay, so Q, okay, okay, so I told you that the current across the capacitor is changing like this. Okay, current across the capacitor is changing like this. Okay, so you can see that the Q is equal to IT. Okay, Q is equal to IT. The current is multiplied by T, it is equal to Q. Okay, for example, let's say that there is a conductor. Okay, there is a conductor, and the current, okay, and it is said that, okay, so let's say that the current, okay, current through this conductor, okay, current through this conductor is 5 volt, 5 ampere. Okay, so current through this conductor is 5 ampere. Okay, and this current is flowing, this 5 ampere constant current is flowing 2 seconds through this point. Okay, through this point, 2 seconds through this point. Okay, so okay, so if I ask you what is the total charges flowing through this point up to 2 seconds, so there are 5 ampere current and it is flowing in 2 seconds. Okay, so total charge will be 10 coulomb. Okay, so that is ampere second, another value for the charge, that is ampere second. Okay, okay, I think this is a charge density, no? Okay, this is also should be divided by A. Okay, if you consider a conductor, this I is defined as rate of change of charges per unit area. No, I think that is the correct one. Okay, but we no need that one. Okay, we no need that definition, correct definition. Okay, so this is given in some area. Okay, if this is given in some area, so through that area this 10 coulombs charges is flowing. Okay, so that is the way. Okay, so simply you can if the current is constant, you can multiply this current, multiply the current by the time, and you can find the total charges. Okay, so that is the idea what I want to give you. Okay, so if the current is constant, okay, through this time, okay, and you can simply multiply the time by current, then you can get the charges. Okay, but when it comes to capacitor, okay, the current is not constant. Okay, current is not constant, so it is reducing like this. It is not constant, it is reducing. Okay, so if you want to find the coulomb or charges up to this total charges at some point at T1, so what we should do? මොකක්ද අපි කරන්න ඕන? දැන් current එක constant නම් time එකත් එක්ක හරි අපි හිතන්නකෝ 5 ampere ගියා තප්පර දෙකකදී. හරි අපිට කියනවා කූලෝම් ගාන හොයන්න කියලා. ඒ ඒරියා එක හරහා ගියම කූලෝම් ගාන හොයන්න කියලා. හරි මෙතන මේ current එක මට මතක හිටියේ සමහරට මේ unit area එකකුත් එනවද කොහෙදනේ? මට හරියට මේක මතක නැහැ. හරි හරි කොහොම හරි අපි හිතමු දැන් මෙතන A කියන එක 1යි කියලා. හරි A කියන එක 1යි කියලා හිතමු. හරි මට ඒක හරියට මතක නැහැ. හරි මේ QAT okay පොඩ්ඩක් පුළුවන් නම් බලන්න. Okay, you can refer the internet or you can refer your note, maybe your A-level notes are not there, no? So you can refer the internet and you can verify this equation. Okay, but for our discussion that is enough. Okay, so I want to give you this idea. Okay, so if the current is a constant, okay, if the current is a constant, so you can you can find the total coulombs by multiplying this current by the time. ඒක හරිනේ. current එක time එකෙන් වැඩි කරලා කෙලින්ම coulomb ගන්න හොයන්න පුළුවන්. ඒක තේරුණා නේද? මේ සරත් මේ sorry කුමාර්. ඒක ඕකේ නේද? hello okay හරි anyway okay so so now the current is not a constant. Okay, current is not a constant. Okay, so if you want to find the coulomb up to this, the charges up to this point, so what we have to do? Okay, so this current is not a constant. Okay, so if the current is constant, you can multiply this current by this T. In other words, you are finding the area of this area of this section. Okay, so this T like this. Okay, and if the current is a constant like this, okay, up to this T, if you want to find the coulomb, okay, so you can multiply this number of coulomb by T and you can get the now the current by T and you can get the total coulombs, total charges. Okay, so that means in other words you are find the area of this section. Okay, so here also to find the coulombs you have to find the area of this section. Okay, to find the area of this section, what we have to do? We have to integrate this IT from here to here, no? Okay, to find the Q, then we have to integrate this IT from here to here. Okay, so QT is equal to integrate 0 to T1, let's say that T1, and it is IT dt. Okay, because this IT is not a constant. This is a simple line. Let's say that this is a simple line. Okay, so you have to do the integration. Okay, because this I is not a constant. Okay, so Q2 is equal to this one. Okay, so again you can come to this one. Okay, come to this one. Vt equal to Vt is equal to 1 by C Qt. Okay, 1 by C Qt. Okay, and instead of this Q you can put this value. Okay, then Vt is equal to 1 by C 0 to T1 IT dt. Okay, so you can get this expression. Okay, so this expression is valid. Okay, if this expression is valid, if we charge the capacitor from the initial. Okay, that means, okay, so if you get a capacitor, new capacitor, okay, and you just discharge all the charges, okay, you can short circuit and you can discharge all the charge. So if you get the capacitor like this, okay, if you connect these 2 points, if the charge is there, it will be discharge, and the charges will be come to 0. Okay, so there are no any voltage difference between this capacitor. Okay, and at that time, okay, so that is a new capacitor, there is no any charge. Okay, so if you connect that capacitor between a battery, okay, and if you switch it, okay, if you switch it when there is no any charges, initial charges in this capacitor, okay, initial charge of this capacitor, so this voltage current varying is valid. Okay, but what happen if we have initial charges at the capacitor? That means you have used this capacitor for some time, okay, and you have closed it. Okay, so that this capacitor is charged up to some level. Okay, so that means, okay, okay, so T, and this is Vt. Okay, now let's say that this capacitor has initially some charges. Okay, initially charges. Okay, so that means it has an initial voltage value. Okay, if there is some charges, it has an initial voltage value. Let's say that it is V naught. Okay, okay, V naught. Okay, so some voltage level is there, V naught. Okay, now if you switch this, okay, if you switch this, okay, if you switch this, this is, okay, if you switch this, okay, let's say that you are switching this at T naught time. Okay, so initial voltage is there, and you have done this switching at T naught. Okay, so at T naught, it will start to again charging. No, it is again charging. Okay, the capacitor will charge again. Okay, so the voltage will be increasing like this at this point. Okay, and once it's come to maximum level, the voltage value will be constant. Okay, so from here to here it is charged. Okay, now if you want to find the charge at this point, let's say that it is T1. Okay, so you have to consider this voltage value. Okay, but it is not there. Okay, so so um, so this is the 0 time, and this is the starting time. Okay, and normally this time cannot be a minus value. Okay, but if we refer some time as 0, the previous time we can consider as minus, and the future time we can consider as plus. Okay, so here if you consider some time, okay, at 0 you have considered some time, and there can be some previous time also. So that times, the total times range will be minus infinity to 0. Okay, so you at T naught you are going to charge this capacitor. Okay, at the T naught also, at T naught there is a charge. Okay, that means from minus infinity to T naught there is a charge. Okay, minus infinity to T naught there is a charge. Okay, and then T naught to T1 you want to find the new charge. Okay, so you can modify this one Vt. Okay, 1 by C. Now you have to find the charge from T naught to T1. Okay, from T naught to T1. So that is IT dt.  'Okay, 'T', 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 you have an initial charge that due to that charge you have another voltage. Okay, so that is V naught. Okay, so V naught plus voltage up to this. Okay, so here this refer the voltage increase between these 2 points, this point, okay, this point and this point, this point. Okay, so the voltage increase and the existing voltage, okay, exist voltage plus the increased voltage is the total voltage VT. So this is the exist voltage and this is the increased voltage. Okay, so you have to add this the exist voltage to the increased voltage, then you can find the total voltage across the capacitor. Okay, so we are interested of this uh, expression. Okay, so this expression is given. Okay, so this is one expression to characterize the capacitor. Okay, capacitor. So this is very important. Okay, so others are so this so I explain how we can come to this point. Okay, how we can come to this point. Okay, but this one is the most important one. Okay, so you can use this equation to characterize a capacitor. Okay, okay. Is that okay? If you have any problem, please ask. Okay, so this V naught is the voltage from minus infinity to 0. Okay, we don't know minus infinity to 0. Okay, so we can consider like this. Okay, and there is another equation we can get from this equation. Okay, so we can somehow terminate this integral. Okay, to terminate this integral, what we have to do? We have to differentiate this. Okay, okay. So if we differentiate with respect to t, okay, I will get dvt divided by dt is equal to 1 by c. Okay, and this integration will be cancelled. Okay, so you will get it plus this is a constant. No? So if you get the integration of this v naught dv naught divided by dt, you will get a 0. Okay, so using this expression you can derive another expression. Okay, you can derive another expression, that is it is equal to c dvt divided by dt. Okay, so these two expressions you can use to characterize a capacitor total. Okay, so you can use this expression to characterize a capacitor total. Okay, so is it okay up to this level? Do you have any problem? Okay, if you have any issue, I can explain. Okay, okay, so I hope it is okay for you. Okay, so if any problem is there, please stop me and ask. Okay, makari ප්‍රශ්නයක් තිබ්බොත් අහන්න. Okay, so these are the most important equation we need. Okay, so normally when the I is given, okay, so normally so that may be not applicable for every problem. Okay, so normally the current is given, it given, and if we want to find the voltage, okay, so normally I use this equation. Okay, so sometimes we at once we can't think. There are two equations. Which equation we can use? Okay, to get a to solve a question easily. Anyhow, we can use any equation to solve any problem, okay? But if you use this one or this one, okay, so at some time this equation may be easy. Let's say that this is equation 1 and this is equation 2. At some point, this equation 1 may be easy, and some point this equation 2 may be easy, okay? So we may have a confusion which equation we should use, okay? The 1 or 2, okay? So normally, if the I is given and if you want to find the voltage, normally I use this question 1, okay? Equation 1, okay? And if we are given the voltage is given, and if we ask to find the current, normally I use this equation 2, okay? So we will see. So most probably it will, in most cases, it will be okay. But sometimes that approach may be not good, okay? But you can have that kind of idea how to occasionally choose this equation, okay? Okay, we will go forward and we will try to figure out, okay? So I want to tell you one thing, okay? So can you tell me, okay? Can you tell me if we given a constant voltage, okay? If we given a constant voltage, so we are given a constant voltage, okay? And this is already charged, okay? Already charged, that means the voltage is not changing anymore, okay? So if it is at a constant voltage, that means voltage is not changing, okay? So it is a constant voltage, okay? So at that time, what is the current? Can you tell me at that time what is the current? Actually, we have seen this before, okay? If the voltage is not increasing or decreasing, there should not be a current, no, flowing through that capacitor, okay? The current should be 0, okay? And you can use these two equations to explain that one, okay? So which one can you use, okay? So you can see that, so you are asking what is the current, okay? So you are asked to find the current, okay? And constant voltage, that means you are given the voltage, okay? So at that time you can use this one, equation 2, okay? So the current is equal to C dVt dt, okay? So if you differentiate any constant with respect to t, it will be 0, no? If V is some value, constant value, if we differentiate it with respect to time, the value will be 0, okay? So the current also will be 0, okay? So that is one case actually, okay? That is a one case, okay? Okay, so I think that is enough for the explanation of the capacitor, okay? But when we are using, okay, another thing is the power, okay? Another thing is the energy between the capacitor, okay? Energy between the capacitor, okay? Between the capacitor. Energy across the capacitor, okay? So we will check that one also, how we can figure out that one, okay? So energy between across the capacitor, okay? Energy of the capacitor, okay? So so if the resistor is there, okay, and if you connect the voltage across the resistor, you know that the voltage, when the voltage increasing, the current I is increasing in this way. Okay. And if you find the energy, okay, if you find the energy, okay, so you know that power is equal to VI, okay. So if you want to find the energy at some time, okay, let's say that it is at time t1, okay, from 0 to t1, okay. So you have to, so this is the power, okay, and if you multiply it with the time, you can get the total energy, okay. You can get the total energy, okay. You can get the total energy, okay. Power, so power is defined by energy per 1 second, okay. So if you divide energy per second, you will get power. Then the energy is equal to power into time, okay. So you have some power, that is VI, and you give that power from T1 duration. So the total energy dissipated through this resistor will be VIT1, okay. So that is the total energy, okay. So it is measured in joule, okay. The power is measured in watt, okay. Watt means joule per second, okay. This is watt, okay. Power is measured from watt, okay. So what is joule per second, okay. Joule energy per 1 second, work done per 1 second, okay. So that is the total work done by the resistor, okay. So resistor will dissipate that kind of number of energy, joule, amount of joule at that time, okay. So if you consider capacitor, okay, actually it is somewhat hard to draw the VI characteristic of the capacitor, okay. So you can use that one, okay. IT is equal to C dVt by dt, okay. So you can see that IT is there, that is the current, okay, and the voltage, it is a voltage, what is that called, the gradient of the voltage, okay. So dV by dt is the gradient of the voltage, okay, and you can get the current and gradient of the voltage as linear one, okay. But if you want to get the voltage with respect to IT, okay, so that is the voltage and VI characteristic, voltage and current characteristic, it is somewhat complex, okay, because the integration is also there, okay. So you can plot this for different cases, okay, for different value. You can use some different value and you can use these two equations and you can plot the VI characteristic using MATLAB like software, okay, in MATLAB or Python, okay. So you can check it, okay. So now no time, later I will show you if you are interested, okay. So we can plot this VI characteristic for some cases with the values, okay, with the values, okay. So we will see it later, okay. Okay, anyway, so that is, so this is the VI characteristic of the capacitor we are given in this way, okay. So anyway, okay, so you know that the current is varying with respect to time in like this, okay. This is the current IT is varying with respect to time in this way, and the voltage is varying this way with respect to time, okay. So you know this, okay. Now you want to find the energy at some point, at some time, T1 or T2, T1 or sometime, let's say that it is T1, okay. So the power is the same. So you can use this equation to find the power, okay. So that is VT into IT, okay. So this is the power at that instant, Vt into It. That is the power. Okay. Okay. And Vt, It, and you have to divide, you have to multiply it by T. Okay. So here you, so you have multiplied it by Vi and you have multiplied it by T. Okay. So this V and I are constant with respect to time. Okay. At time instant, this V and I are constant. Okay. So this is not changing. Okay. Okay. So, but here, these are not constant. Okay. These are changing. Okay. So if you want to find the total energy between a capacitor, you have to again, as in this case, okay, as in this case, as I have explained in here, you have to again integrate. You have to again integrate this, okay, from up to this T1. Up to this T1, you have to integrate. Okay, so so we are not starting from 0. Okay, because sometime this 0 may be another reference value. Okay, we don't know. Okay, so normally we will do the integration, so from minus infinity up to T1. Okay, so the total energy of the capacitor, okay, capacitor can be found, okay, using, if you integrate minus infinity to some T value, let's say that it is T1, okay, up to T1, okay, so you have to integrate this Vt with respect to dt, okay, up to this point. Okay, so you will get like this. Okay, so 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 you can write this I in terms of V again. Okay, so It is equal to dV by dt. Okay, so you can you can replace this I using this expression, so you will get minus infinity to T1 Vt dVt by dt. Okay, okay, and dt. Okay, so in this way you can get. Okay, so this is Vt dV. Okay, dV by dt. Okay, so okay, so you can find, you can get like this. Okay, and you can see that this dt cancel out and you will get Vt into dV. Okay, Vt into dV. Okay, so this V is a function of time. Okay, V is a function of time, but now it is changed into voltage domain. Okay, it is changed into voltage domain. Now time domain is not there. Okay, so it is in voltage domain. Okay, so you can do the integration, but you have to change this limits again. Okay, so here now you are going to change the integration domain. Okay, the independent variable, you are going to change the independent variable. Okay, I think we have done this kind of question. No, okay, so you have to find the voltage. Okay, you have to find the voltage, this minus infinity and T1. Okay, so because now you are changing this time to voltage. Okay, so dt cancel out and we get voltage dV. Now we are going to integrate with respect to V. Okay, now these are time values, this minus infinity and this T1 are time value, and you have to change this into voltage also. Okay, so what is the voltage as minus infinity? What is the voltage as minus infinity? Minus infinity means at the beginning. Okay, so it is the initial. Okay, so at that time, okay, there is no any voltage. Okay, so at the minus infinity, it will be 0. The voltage is 0, definitely. Okay, but at 0, we can't say that we can't say that equal to 0. It is not equal to 0. It may be not equal to 0 because if there are any charge, okay. Okay, so but this is the minus infinity is the ultimate starting point, okay, not the reference point. Okay, it is ultimate starting point. At the ultimate point, there should be no any charge in the capacitor. No, is that clear for you? ඒක තේරුණාද?
ඔව් සර්.
හරි, minus infinity වල කොහොමදක් තියෙන විදියක් නැහැ. මොකද ඒක අර ultimate එහා පැත්තෙම තියෙන value එකක් කියලානේ ගණන් ගන්නෙ. හරි. එතකොට එතන අනිවාර්යයෙන්ම voltage එක බිඳුව වෙනවා. එහෙනම් we can replace this minus into voltage value, that is 0, and let's say that at T1 the voltage is VT1 or something. Okay, so this VT1 is a constant. Okay, so that is the thing you should understand. This VT1 is the constant. So the time, any constant, it is not a constant. Okay, at that time it is a constant. Okay, this T1 time it is a constant. Okay, so if we integrate this, okay, so now we have a fine integration, that is 0 to V T1. Let's say that it is capital V or something. Okay, so this is the voltage at T1. Okay, any time. Okay, and it is equal to V. Okay, I didn't write this T. Okay, I am not writing this T because it is not not relevant to this equation, because now this is in voltage domain. In dV domain, the variable is voltage, so time is considered as a constant. Okay, so here you have two variable. Okay, you have two variable, time and voltage, but now we are going to integrate with respect to voltage, so we have to consider time as a constant. Is that okay? No, that is okay. No, okay. So I just drop this t value. You can put the t value, no issue, and you will have this one dv. Okay, and there should be c. No, yeah. When you replace it, I t dv by dt, it is c dv by dt. Okay, so c is there. Okay, so c is a constant also, and the c is there also. Okay, and I get that out c. Okay, so I get this value. Okay, so if I integrate this, I will get v square divided by, sorry, v square c, v square divided by 2. No, v square divided by 2, because I integrate it with respect to v. Okay, so it is v square divided by 2, that is 0 to some voltage value. Okay, t at the t. Okay, let's say that it is v1 or something, because v is also there. No, let's say that it is v1. Okay, and this is multiplied by c, this c also there. Okay, and the energy you will get half c v1 square. Okay, so this is the energy, total energy. Okay, okay, so that means if you are given a capacitor and it is said that there are 5 volt across this capacitor, and the capacitance is 10 microfarad or something, if you are trying to ask the energy, okay, energy of this capacitor, you can easily find it half c v square. Okay, so half is there, c is 10 microfarad into v square. V is now 5 volt. At 5 volt, if you ask to find 2 volt, you have to put 2 volt here. 3 volt, you have to put 3 volt. Okay, so we are asked to find it at 5 volt, so it is 5 square. Okay, so you can simplify and you can get the energy. Okay, so that is the energy of the capacitor. Okay, so we have discussed the VI characteristic of the capacitor, how V and I are relating with the capacitor, and we have find the power of the capacitor. Okay. Okay, and this one also we need to discuss. Okay. So, okay, I think that is very easy. Okay. Okay. We will see. Okay. So, let's say that if we have uh, in our electronic component, sometimes we have to connect the capacitor, uh, two or three capacitor in series or parallel. Okay. So if you connect a capacitor, some capacitor in series, okay, so we will see how to get the equivalent series capacitance. Okay. Series capacitance. Okay. So you have to use the same procedure when you are finding the equivalent capacitance of the resistor. Okay. So we will see. Okay. So let's say that serially we have connected several capacitors. Let's say that we have connected n capacitor like this. Okay. So this is the first capacitor, third, second, third, and this is the nth capacitor. Okay. And we have connected it between a voltage. Okay. To some voltage value. Okay. Let's say that voltage is V. Okay. Okay. So if you consider the, so this V also change in, okay. So we can say that V is Vt. Okay. So this is the voltage between the all capacitance. Okay. So let's say that voltage across this capacitance is V1t, this capacitance is V2t, this capacitance is V3t, and this capacitance has Vnt. Okay. So the voltage should be changed. Okay. Let's say that this is C1, this is C2, this is C3, and this is Cn. Okay. So the capacitance is changed. So voltage should be changed. Okay. So you know that if this is serially connected, the current through all the capacitance should be same. No, the current should be same. Okay. If it is serially connected, current should be same, but voltages are not same. Okay. Okay. Now we will try to find a expression for the equivalent capacitance. Equivalent capacitance means, okay, if you replace this all capacitance by one capacitance, okay, okay, and the value of this capacitance, okay, that is the equivalent capacitance. Okay. So the voltage should be Vt, okay, the same voltage, and current should be the same current It. Okay. Okay. So okay, now if I write the current, so you can see that now current is same. Okay. And there are voltage, different voltage. Okay. So we can write this V, the total voltage across the capacitor bank, okay, of all these capacitor is equal to V1t plus V2t plus V3t Vnt. This is okay, no? Okay. So the voltage can be considered like this. Okay. V1t, V2t, V3t like this. Okay. This is V1t. Okay. This is V1t. Okay. This is T. Okay. This is T. Okay. V1t, V2t, V3t up to Vnt. Okay. So I is constant. Okay. Now you can see that I is constant. Okay. It is say that it is just like we are given I. We are given I and we need to find Vt, no? It is in this case, no? Because Vt is equal to V1t, V2t, V3t like this, okay? So we have to find this V1, V2, V3, okay? And I is constant. That means we can say that I is given. It is not actually given, but we can assume like this, okay? So what equation is it easy to use? Can you say that? equation 1 or 2? Equation 1 is Vt is equal to 1 by C T naught to some T value IT dt plus V naught. This is the first one. And the second one is IT is equal to IT is equal to C dV by dt. Okay. So this is the second one. Okay. So, what equation we should use? This one first equation or this second equation? This is the first equation and this is the second equation. Okay. So what is the equation we should use here? Can you get idea? So I told you that when the I is given, and if you want to find the Vt, it is easy to use this first one. Okay. And the V is given, and if you want to find It, it is easy to use this one. Okay. Equation 1 and equation 2. Okay. So here, in this case, we can see that, okay, I is somewhat given, no, because it is constant, and we have to definitely find the V terms. Okay. So what is the equation we should use? We should use 1, no, first equation, because it is easy to use the first equation if the V is given, sorry, I is given, and need to find the V. Okay. So for each capacitor, okay, each capacitor, I use that equation 1. Okay. So if I use this equation 1 for the first capacitor, it is V1T is equal to 1 by C1 integrate 0 to, let's say that T naught to T1 IT plus, let's say that the initial voltage is V V1. Okay, let's say that is V1. Okay, and I put the second. I put that same value for the second one also. So it is V2T is equal to 1 by C2 T naught T1 IT plus V2. Okay. Okay. So this is first one. This is second one. Okay. And the V3 also I can write the same expression. It is 1 by 3T T naught to T1 IT plus V3 something. Okay. So for the N1 also, I can write VNT is equal to 1 by Cn T naught T IT Vn. This, so this is the nth term. Okay. So if I add this whole expression, I will get this V1, V2, V3, Vn, that is equal to V, no? So that is equal to V. Okay, Vt. Okay. So Vt is equal to, so you can see that here 1 by C1 ITV1, 1 by C2 ITV2, 1 by C3 ITV3. Okay, so we have to add them together all. Okay, so I can use that sum notation. Okay, so I use this sum notation. Okay, and I put simple n as the variable. So simple n should be 1 to capital N, no, because these are changing 3n like this. Okay, so this is n equal to 1 to n. Okay, and I can write this as 1 by Cn, okay, T naught T, see this is capital simple N, okay, so this is a bit simple N Okay, Cn T naught T IT, okay, plus all these also add in, no, V1, V2, V3 up to Vn, okay. So I add them, okay. So V1, V2, likewise up to Vn, I add, okay, we have to add, okay. So what is this value actually? V1, V2, Vn. So that means the initial value, okay. If that will be the initial value, okay. Initially charge value, okay. So here we have V1, V2, V3, V4, okay. So that value is the initial value. Let's say that it is V naught or something, okay. So V naught is equal to V1 plus V2 plus V3 plus like this, okay. So this is the initial voltage across this band, okay. So that is the initial total voltage, VO. That is the initial total voltage. This is initial total voltage. Initial total voltage, okay, across the capacitance, okay, V naught, okay. So if you consider one capacitor, that initial voltage also should be equal to this one, no, because you are finding the equivalent capacitance for this band, okay. So you are finding V naught, okay. So here also it is equal to V naught, okay. So that V naught means V1, V2, V3, V4, V1 plus V2 plus V3 plus V4, that is the initial total voltage across the capacitor, okay. So this is the initial total voltage across the capacitors, okay, capacitors, okay, and it is equal to, let's say that V naught, okay. So we say that it is equal to V naught, okay. So if you consider resultant capacitor, so that one also should have the V naught initial charge, okay. So now I am going to put this equation, the first equation, to the resultant capacitance, okay. Let's say that it is 1 by Cs, sorry, let's say that it is Cs, okay. So this is the equivalent, okay, Cs, okay. So if I write the voltage current combination Vt, okay, so this Vt is equal to this Vt, is equal to 1 by Cs T naught to T IT, okay. So this IT is equal to this IT, and this T naught and this T both are same, all are same, okay, plus V naught. And this V naught is equal to this one, V1 plus V2 plus V3 plus up to Vn. So this is V naught, okay. So this one and this one equal. So you have to find this Cs, 1 by Cs. So you have to equal these two terms, no, okay. You can equal this one and this one, okay. Let's say that this is 1 and let's say that this is 2. So if you equal this 2, you will have n equal 1 to capital N, 1 by Cn, this integration, okay. So that integration, if you do integration from T naught to T, some T, okay, and this is dt, you will get some value, okay. So you will have a value here, plus you will have the V naught here, and that is equal to 1 by Cs, okay. And the same value should be there, no, okay, because here also you are going to integrate from T naught to T some value, that is IT dt. This I and I same, this T naught and T, this T naught and T are same, so you will get the same result here, okay, some result, okay. So this result and this result will be equal, okay, and it will, and plus it is V naught, okay. So this V naught and this V naught equal, it is cancelled out, and this result also equal. So it also cancel out. Okay. So finally you will get, okay, 1 by CS is equal to n equal 1 to capital N 1 by Cn. Okay. So this is the expression for serially connected capacitors. Okay. In other way, 1 by Cs is equal to 1 by C1 plus 1 by C2 plus 1 by C3 up to 1 by C10. Okay. So this is the expression you should remember. Okay. You should remember this. Okay. But if we serially connected the capacitor, sorry, resistor, it is, we get it is like this, no? R serial equal R1, R2, R3 up to Rn, like this. Okay. But here we have the reciprocity, no? Okay. Okay. 1 by value, just as in parallel resistors. Okay. But this is for serial. Okay. This is for serial capacitor. Okay. Capacitor. Okay. So you can remember it like this. Okay. If you remember the resistor value, you can remember that it is other way around. Okay. It is other way around with compared to the resistors. Right? Is this one okay? Make okay.
Oh, sir. Okay.
Okay. So next we have to find the parallel. Okay. So I will stop here because we have already running out of the time. Okay. So anyway, I think you can try this at home. Okay. So then you can refresh and you can get a good idea. Okay. So try to get the resultant capacitor value, resultant capacitor value for parallel connected capacitor bank or something. Okay. So I will give you some hint. Okay. So if you have parallelly connected, okay, so those are like this. Okay. Right? So this is parallelly connected. Okay. And so you know that the voltage will be same, no? The VT will be same for all the capacitors, okay? Because they are parallelly connected. But I will be changed, no? So if you have total IT here, okay? So this one have I1T, this one have I2T, this one have I3T, like this one have I4T, okay? And if there are n capacitor, okay, this will have INT. Sorry, INT, okay. And this is C1, this is C2, this is C3, this is C4, this is Cn, okay. So you can see that the voltage is constant, okay. This is constant, okay. And the total I is equal to I1T plus I2T plus I3T up to INT. Okay. So if you consider a resultant one, okay, resultant one, this one, so this is the resultant parallel one, CP, let's say that it is CP, okay. So this VT is same and this total current also same, IT, okay. And so you have to first find the expression for the IT for the total band and expression for the IT for the this one, and you can equal that one. Okay, then you can find the one. Okay, so in this case, it is just like we know VT. We know VT because it is constant, and we need to find IT. need to find IT. So at that time, which equation is easy to use? Equation 1 or equation 2? Okay, so you can decide.
Equation 2.
Yeah, very good. We have to use the equation 2. Okay, so try to use the equation 2. Okay, so when you are using the equation 2, it is somewhat easy because you no need to consider the initial voltage, because for that one, okay, it is a derivation. No? So initial voltage is normally a constant. So when we get that 2 1 to the equation 2, yeah, that one. This one, there is no this term, no? This term is not available, we know, okay? So you can consider the current values, okay? So you can, I think you can get easily the expression for that one, okay? So try to get it, okay? Try to get it, and so try to go through this lecture and try to figure out these things, okay? And let me show you the SLTs. Okay. Okay. So we are referring this one, okay? This lecture note, okay? Okay. So this is your note, okay? And these things we have discussed, okay? So you can refer this note also, okay? So I think all are clear now. And you are given some exercises, okay? Try to do these exercises by yourself. If not possible, okay? I will explain in next one. We will do some exercises, okay? And this is series capacitance. Okay, this is for parallel. Okay, and we have some exercises also. Okay, so we will do these exercises. So first try to do this by yourself. Okay, then I will do this. Okay, these are very simple. Okay? And finally we have to consider about the capacitance charging. Okay, so we have already discussed these things. Okay, but when we find this capacitor charging, we have to get a differential equation. It is a first order differential equation, and you have to solve it. Okay, so you have to solve it and you can get this value. Okay, so try to do this one also. Okay, but you need to know how to solve a differential equation. But next week we will see this. Okay, so if you have time, try to do this exercise by yourself. Okay, otherwise we can do this in next week. Okay, so we will stop here. Okay, so if you have any problem now, you can ask. How the